Hi, everybody. I hope you guys are having a great day. Today's lesson is lesson 28. It is for March 27th, 2020. I thought I'd introduce you to our little guest lecturer today. Jeanette's going to be hanging with us. So I just wanted to say hello. I'll switch over to the lecture notes, and then we're actually going to do a bit of a PowerPoint presentation for the lesson today. All right, so just a couple quick admin things. So today is sort of our first trial run of submitting assignments in Blackboard/email. So as a reminder, homework 7 and in-class 7 are both due to me by 11:59 p.m. Eastern time. So if you can upload it to Blackboard, that would be great, or if you can email me. Ideally, if you can scan and send me a PDF of your work. But if that's causing an issue, totally fine just to send me a photograph of the homework assignment pages and in class 7, just as long as I can read it. Although I will say here too, please, if you can take a look at the solution and try to note any places where we might be different, or if you have any specific questions, that would be really helpful. I'm not exactly sure how grading is going to go, kind of looking at a solution that's on a computer and like providing feedback. So just sort of let's both try to have a look, and hopefully that will be pretty good. Also, as a reminder, exam 2 is scheduled for next Wednesday. I'll be posting that on Blackboard. I'll have a review lecture posted on Monday the 30th. And in terms of what that covers, so basically everything from the direct stiffness method as it applies to beams and frames, so considering horizontal, vertical displacement, and now rotation. As well as STAAD. Again, since we're sort of off campus right now, I would say be familiar with the basic principles. I think looking at those dialog boxes like in class 6 and you'll see on the practice exam should be very helpful for that. And then finally, what we've done most recently with API design guidance. So the whole relevant homeworks are homeworks 5, 6, and 7, and the associated in-class problems. Last time we finished up our API example 2, with our Lake Erie diving platform. That is going to be the last lesson that you'll be responsible for Wednesday's exam. Today, we're going to introduce environmental loading. This is new material. This is sort of the last big objective we have for this course. So we've talked about what are the deformations once you have the loads. Once you have the loads, is your structure safe? And finally, we need to determine how do we get the loads. So I think there's a lot of background information today, so I think it might be easiest to sort of go through a PowerPoint and then fill in the blanks. I'm going to go ahead and share my screen. And let's see if I can go ahead and start the PowerPoint. Great. And then I'll expand this little dialog box, and I'm hoping that what I can do is sort of take notes on the side without interrupting too much of what's going on the slideshow. And then it'll be small, but, you know, I think, you know, I'll have these posted after the lesson too. Your eyes are also better than mine. So at any rate, let's go ahead and just get started. So again, so far, we've calculated what the effect of any load or moment that is applied to a structure would be. And so again, what is the effect of this load and moment on joint displacements or rotations? Also, what are the support reactions? And again, we can do that for statically determinate or statically indeterminate structures with the direct stiffness method. And then also, what are the internal member forces? And we used the direct stiffness method to do this by hand. And we also used the computational program STAAD to calculate this a little bit more quickly once we had the structure set up in STAAD. In addition to finding these displacements and reactions, we also have assessed whether a structure is safe. So we assess the safety of a structure using API design criteria. And really, we could have used any design guidance here. We could have used American Society of Civil Engineers. There's other codes that are out there, the International Building Code. The API design criteria is nice because it applies specifically to offshore. And since we have ocean engineering structures, it makes sense. So the very last question is, how do we get the loads? So take a minute and think about what loads you might expect on an offshore structure. I'm gonna wait about 10 seconds, but feel free to pause if you're having fun brainstorming, and go ahead and jot them down in where the notes are. All right, that was a quick minute. So some typical loads that an offshore structure might experience. We have debris loads. So any debris that would be floating in the ocean could impact a structure, and you need to consider what that impact might do to the structure. Also, depending on where your structure is, you might have to deal with ice loads, also seismic loads. You have current, you have wind, you have waves. You might have thermal expansion. And then also you have the self-weight of the structure, which is what we call dead loads. So self-weight of the structure, as well as live loads, which would be due to things that are moving around on top of that structure. So something like people who would be expected to be on that structure, any machinery that might not stay put. Typically, these are represented in terms of pounds per square foot, and you apply it over the whole floor, just in case you have people sort of all in one area of the structure. For this class, we're going to focus on wind, waves, and current. So we'll focus on wind, waves, and current. As you can see in this simplified diagram 3.1. Again, wind is typically going to act above the still water level. You guys, have talked about how waves can interact with piles and how waves can interact with structures in your waves class. And then also currents, which we can estimate using hydrodynamic loads from our fluids principles. Let's start off talking about wind loading. And before we can talk about the wind load, let's define sort of how we determine wind speed. So the first definition is the fastest mile of wind, which is equivalent to the highest wind speed in one day. And what do I mean by a mile of wind? So the definition of a mile of wind is the speed associated with the average time it takes a horizontal column of wind 1 mile long to pass a measuring station. So the speed associated with the average time it takes a horizontal column of wind 1 mile long to pass a measuring station. And typically we measure these wind speeds approximately 10 meters or about 30 feet above the ground or mean sea level. So I'm kind of blocking mean sea level there, but if you're in the ocean, you don't have ground, so that's why we would use mean sea level. Okay, so we can record the wind speeds at any given moment in a day. The next question is, what wind speed should we use when we're actually designing our structure? So what wind speed to use? A lot of times, daily records at a monitoring station can be analyzed using statistics to find the fastest mile of wind in a given year. And if you have a long enough record, you can start to calculate exceedance probability. So what's the likelihood that I have a wind speed of X being exceeded in any given year? So we can start to calculate exceedance probabilities. Generally, the longer your record, the better. And with these exceedance probabilities, you can start to create these maps for design. So these are the wind speeds that you might expect when you're designing a structure. So we have the simplified figure that we can show here on the left side. This is also in the notes. This is what we'll typically be using for the problems that we have with respect to design. This tells the annual expected wind speeds with a 100-year recurrence interval at various near shore locations in the United States. So for example, if you're off of the coast of Oregon, you might expect a wind speed of 100 miles per hour. That would be your 100-year wind speed. So it has a 1% chance of being exceeded in any given year. Moving over to the Gulf of Mexico, sort of around Texas, Louisiana, we have a 110-mile 100-year wind speed, or 1% annual exceedance probability. These maps can be very complex. So here's the American Society of Civil Engineers wind speed maps in their building guidance for residential and other structures. And you can see they have all of these different contours with wind speeds all around the United States. And so they have, I think this is just one figure of many where they talk about different recurrence interval wind speeds. Again, typically we'll use the 100-year recurrence wind speed for the 100-year. Although I will say that especially with respect to flooding, people have started moving up to the 500-year wind speed just because we're starting to see effects of climate change, sea level rise, etc., more intense storms. Really important is that the 100-year recurrence wind speed is not a wind speed that will only occur one time in 100 years. I'll move this video down a little bit. So it's not the wind speed that occurs once in 100 years. It's the wind speed that has a 1% annual exceedance probability or a 1% chance of occurring in any given year. So if I start to combine the years together, so if I start to think about, okay, well, what's the chance that this wind speed happens in 5 years or 10 years or 50 years, that 1% annual exceedance probability starts to, be a larger probability of happening in 50 years. So for example, a wind speed that has a 1% chance of occurring in any given year has over a 60% chance of occurring over 100 years. How do they get these numbers? So let's do an example for the Maryland coast. So the probability of having a 130 mile per hour wind speed in any given year. So the probability that I have a 130 mile per hour wind in any given year is equal to 0.01 or 1%. This means that the probability that I don't have that wind speed, so that all my winds are slower than that, so that the probability of a less than 130 mile per hour wind in 1 year, this is also in 1 year, is equal to 0.99 or 99% chance that I don't have my 1% annual exceedance probability wind speed occurring in any given year. So if I want to know the probability that I have a 130 mile per hour wind in 20 years, this is going to equal 100% minus the probability that I have a less than 130 mile per hour wind speed all year to the 20th power. So basically I have to have 1 year that has everything less than 130 miles per hour. Right after that, I have to have another year where everything is less than 130 miles per hour. Same with the third year, fourth year, fifth year, all the way up to 20 years. So basically I'm taking 0.99 to the 20th power, subtracting that from 1, and I get 0.182 or 18.2% chance that I will have a 130 mile per hour wind speed off the coast of Maryland over 20 years. And that matches up with our 20-year interval. We have the 100-year wind has an 18% chance of occurring. So again, just rehashing, we have a 1% wind speed of 130 miles per hour in 1 year. So in 20 years, I'm going to subtract the probability that I don't have that 100-year wind speed every single year for 20 years. If I move inland, I can be a little bit less conservative, so I can use the 50-year wind speed, depending on the location you are. The reason you can be less conservative a lot of times is because you have all of this surface roughness due to vegetation, buildings, other things that tend to break up and slow down the wind. In contrast, if you move offshore, you typically have to increase your wind speeds, and in general, you do it by about 10%. And that's because you don't have these same elements that can cause the wind to slow down, that can act as barriers to the wind. So let's go ahead and do an example for the Maryland coast. So again, if I look at my figure 3.2, we have in the near shore, our wind velocity, U wind, is equal to 130 miles per hour. So if I were to tell you that you had to consider an offshore structure, and it was far enough offshore that you felt like there wasn't going to be any roughness, then you have U wind would equal 130 miles per hour times 1.1. So we're increasing it by 10%, which would be 143 miles per hour. And typically all of the offshore structures we design, if we say offshore, you want to increase your wind speed unless specifically told not to. Wind speed also varies with elevation. And in general, so this figure shows the 1 to 7th power law for designing at a height higher or lower than 30 feet. So I'll go ahead and sketch this in the notes, but basically if we have the wind velocity, U wind, in feet per second on my x-axis, my y-axis is going to be elevation. My wind is going to follow this 1 to 7th curve with U wind at any elevation y is equal to my wind velocity at elevation 30 feet, U wind naught, times whatever elevation I'm interested in, divided by 30 to the 1/7 power. And so at 0, I'll have 0 wind velocity. That kind of goes with that no slip condition. And then that'll increase to the 1/7, which looks like this. Again, if I have 30 feet and I read over to find my wind velocity, that's going to be U naught in feet per second. So just defining variables here, we have U wind at any elevation y is wind velocity at elevation y in units of feet per second. U wind naught, or with a little 0 subscript, is equal to my wind velocity at my base measurement height, so at that 30 feet or 10-meter elevation, so at 30 feet elevation. Again, we're in feet per second. And then finally, y is your elevation in feet. And that's because this 30 is due to that 30-foot elevation where you typically measure wind speeds. So make sure that you're careful with units in this equation. Okay, so that's for averaging winds, but there's also sometimes you hear like, oh, it's a gusty wind today. And so to account for wind gusts, if that would be a problem for our structure, basically what engineers say is it's a really hard problem, so let's just add a gust factor, which is sort of equivalent to a factor of safety. So to account for wind gusts, what we do is we multiply our wind speed by a gust factor. And as you can see in table 3.2, it's also in the notes, gust factor is a function of averaging time, the fastest mile of wind, and also gust duration. So for example, if I had the fastest mile of wind, or the wind speed, was reported to be 120 miles per hour, and my gust duration was 5 seconds long, go ahead and go into table 3.2 and write down what you think the gust factor would be. I'll come back in about 10 seconds. All right, great. So going into this table, we have our fastest mile is 120 miles per hour. So I'm going to be reading this bottom row. My gust duration is 5 seconds. So my gust factor is going to be G sub F is equal to 1.12. And I'll multiply this times my design wind speed to account for any effects of wind gusts. Wind gusts can be very important because if the gusts match the resonance frequency of the structure, you can have amplified displacement. So think of the Tacoma Narrows Bridge, that galloping Gertie that had those really big displacements and then eventually failed. Similarly, if you have gusts offshore for your offshore structure, you might have a similar effect if the resonance frequency matches the frequency of the gusts. Typically, the resonance frequency for offshore structures is between 1 to 10 seconds. And so if you don't have any other info, it's conservative to use a factor of safety of about 1.2. But again, if you do have more info, it's better to use that information. That is all I had for you guys today. That's just kind of showing the final solution. So I'll go ahead and stop my share and just say thanks, guys, so much. I hope you have a wonderful weekend, and please don't hesitate to let me know if you have questions. Thanks a ton for all of your patience. I know we've been getting up to speed with online learning, and I'm sure I'll be posting updates for this lesson since I'm recording it a bit early. But have a great weekend, and looking forward to seeing you all in online office hours.